Advanced LAN Configuration Part 2, Spanning Tree Protocol. When I was first starting to teach Cisco, I had to fly out to San Jose, California, and stand up in front of a bunch of Cisco instructors and present from the book of the CCNA course. And essentially the way it worked is I would present one section that I had prepared, and then they would pick a section at random from the book and just make me stand up there and teach it on the fly. And the section that get picked was indeed Spanning Tree Protocol, and the blood just drained out of my face because this is the one topic that got me for years. It was just, it's not a hard topic to get, but so many technicians out in the field struggle to understand what Spanning Tree Protocol is all about. And that's why I dedicated this nugget to Spanning Tree Protocol. We're going to talk about how to use Spanning Tree Protocol the right way. And I'm going to talk about how we should optimally design our networks to work with Spanning Tree. The configuration of Spanning Tree is fairly straightforward. We just have to know how to do it, and the design of it is most important. Understanding the concepts are far more important than the configuration because it's only a few commands. We'll then take a look at Spanning Tree Protocol enhancements. What's been happening in the last few years? Cisco has long since come out with some proprietary enhancements to Spanning Tree Protocol, and those have kind of gone by the wayside. Uplink fast, backbone fast, things like that. Those are going away and are being replaced by this all-new industry standard. We're going to talk about that. And then finally, I'm going to hit the verification, and I call it the show to know, because there's really only one command that you need to verify that Spanning Tree is working properly. And we're going to dissect all the output that that gives us. So let's get going with how to properly design a Spanning Tree Protocol-enabled switched network. A little review before we get going into the full design of the Spanning Tree Protocol. First off, the foundation. Spanning Tree Protocol is a loop prevention mechanism that blocks redundant links in the switch network. So what that means is you're not going to have a broadcast that goes round and round eating up all of your bandwidth, causing a broadcast storm whenever you have a redundant link in place. And this will make a lot more sense when we see the topology on the next slide. Now, one switch in the network will be elected as the root bridge. I always think, I don't know, whenever I see this statement, I think of the Highlander TV show where there could be only one and people died otherwise. And in the same sense, you could only have one root switch in your network, and that is going to be the center point of your network. And I can't emphasize just how important that is, that it be the center point of the network, because down here, the root bridge is going to be selected on the lowest priority plus the MAC address, also called the bridge ID or the bid. That in turn, let me go back to my second bullet, calculates from all switches. All the switches in your network will find the most efficient path to the root. Now, I'm waving my hands in the air because I'm dying to show you a picture. I'm going to show you that in just one second. But before I do, let me just hit these last 2 points. The priority is configurable on any switch from 0 to 65,535, and it's going to increment in increments of 4,096. Now, the default priority on all switches is 32,768. So who will be the root bridge in your network? Well, by default, it will be whoever has the lowest MAC address. And that's not a good thing, because older switches will typically have lower MAC addresses than newer switches. So they will be the ones that end up winning because everybody's priority out of the box is going to be the same thing. The final statement before I show you the picture is going to be about the bridge protocol data units. This is the language of love between your switches. They're going to communicate, they're going to send packets. This is how they tell each other what priority and bridge ID they have, is through the transmission of bridge protocol data units. It's only when the switch stops seeing bridge protocol data units that it realizes that its neighbor is down. This can be closely compared to a hello packet in the routing world. It tells the switches if each other is online. Here's the topology I was dying for, and I wanted to show it to you because it will help me demonstrate so many concepts with the Spanning Tree Protocol. First off, I haven't added any information to the screen right now other than just the links. We have, in this case, what would be considered kind of a collapsed core network. Up at the top, we have access layer switches, and these are providing access to end clients, and it's the same thing on the bottom. In the middle, we have kind of the core of the network. We have multi-layer switches that are handling the routing and the switching for our network. And in this scenario, we have all of these links in place. And true or false? Answer me this. Redundancy is good. Well, true. We want redundant connections. We want this switch to have two connections to both switches. That way, if, a cable goes bad and gets pulled, or a switch goes down, they have redundancy. These clients don't end up losing their connections to all the other workstations in the network and the servers in the network. So this is a good thing. Redundant links like this are good. However, the way spanning tree works is it's going to block some of them. And this is why I needed this topology to demonstrate it. The reason why is because let's say we have a broadcast. This computer sends a broadcast into the switch. The switch is going to receive that, and it's going to send it out every link, because that's what switches do, is they send broadcasts out. Once it sends it out those links, the other switches receive it and send it out those links. It's kind of like a tell your friends things, and it just ends up looping around the network until every switch in the network is looping these broadcasts at the speed of light, and it's eating up all the bandwidth. And that's, a lot of people see it and say, oh, well, that's bad. Well, it's not. That's not half of it. All of the workstations that are connected to this network freeze because their processor is so busy processing those broadcast packets, they can't do anything else. So not only have you crashed your network, you've crashed every workstation on your network until you can stop the broadcast storm. That's the job of spanning tree protocol. And I'd like first to demonstrate a bad spanning tree protocol design. So let's not change anything. Let's plug all these switches out of the box because, hey, they're switches. They do what they do when you connect them. And let's just let the natural root bridge election process take place. In this case, letting the switch natural selection take place, this switch in the upper left-hand corner happened to become the root bridge. What kind of switch is it? We'll say it's a 1900. We'll say it's a 1912. It was kind of budget cuts, which just sitting in our wiring closets, providing 10 megabits per second to all those workstations. This 1912 switch ended up as our root bridge. So what happens? Well, spanning tree protocol design says that all of the switches will then calculate the most efficient path to the root bridge. And it's going to do that by looking at the links that are connected. Now let's say, the 1912, it has two 100 megabit per second links. So these are our two 100 megabit per second uplinks that are going to our multi-layer switch. They're going to calculate these as the root ports. They're going to say these are our most efficient way to get there, and that's what every switch is going to do. Every switch is going to have a single root port, which is the port that it's going to use to transmit to the root bridge. The root bridge will have all its ports considered as designated ports. That's part of its job description, is it will never have any ports blocked. The X's represent ports that did get blocked, ports that spanning tree chalked up and said, you know what, these are not efficient. These are redundant links in the network, and I'm going to block them unless some change happens to the topology, like maybe this link goes down or something like that. Now, you don't get the full effect until, let me do this. Let me slide this picture out and show you by removing the links fully what happens when these ports are blocked. Voila, there it is. Our topology with the blocked ports removed from the configuration so they're not cluttering up our screen. I also removed the labels so we can just see the physical connections that end up working with the spanning tree usage. And just looking at it, let me take a step back, breathe it in. It doesn't look too bad. I mean, in this case, it worked out fairly good. It looks like this one still ended up kind of being a core to our network, even though all of the traffic has to pass through the root bridge. Lucky. And the reason I say that is because in a larger network like we would have in the real world, and I couldn't fit on a slide like this, we would have switches connected here. We had switches with redundant connections going all over the place. And it wouldn't turn out this way, but let me give you an idea of why this ended up being inefficient. This switch, let's imagine, had a workstation attached to it. And it needed to communicate with a server attached to this switch. Now, back in the physical topology, that we showed before, these two switches have a connection together. It just happened to get blocked by spanning tree because this didn't happen to be the most efficient way to reach that root bridge. So here's what's going to happen. This workstation is going to send a packet to that server. It's going to go up to this 1912 switch, which is probably screaming out because it's not meant to handle this kind of traffic. Everybody passes through it. It sends it back down to this multi-layer switch that forwards it down to this access switch and forwards it over to the server. Every packet communicating between this workstation and server has to follow that same path, up and down in the loop we go. And it's really painful to know that we have a physical connection going between these two, where the workstation could just slide directly through to the server down here. So this design, this picture I've painted here, is just a preview of how bad it can get, especially when you grow the network and you begin adding more switches to the network. So what I want to do is I want to take you now on a journey to make spanning tree more efficient. Not only to pick the right switch as your core, to choose one of the core switches, to have everybody use that as your root bridge, but also to efficiently use those links. I mean, guys, look at this. We've got links all over the place, redundant connections that I was drawing out in the other one, and it just got too messy to keep all in one slide. Wouldn't it be great if instead of spanning tree just saying, oh, that's redundant, that's redundant, that's redundant, you know, blocking them, wouldn't it be great if we could load balance? I mean, hey, that cable's just sitting there, right? Why not use some of it? Now, I know some of you are thinking, well, that's not what spanning tree does. Spanning tree finds redundancy and blocks. But there has been enhancements added to spanning tree, and we can now efficiently load balances if you plan it correctly. So let's talk about it. Let me take you back to the original topology that we started working with, where we had all the switches and all the physical connections laid out there. Let me answer a big question some people had. Why is Cisco ditching their ISL encapsulation? It seemed like such a great idea. Well, the reason why is because ISL supported a specific feature that used to not be available. It was called PVST. Most of you know it as per VLAN spanning tree. So you can actually have a spanning tree instance for every VLAN that you have created. Well, the other standard, which was 802.1d, the spanning tree protocol, adopted per VLAN spanning tree, so ISL's usefulness really went away. Here's the beauty of per VLAN spanning tree. We have all these physical connections in this switch network, right? Well, spanning tree by itself, if left to its own, will block all of those links just like we talked about in the previous slides. Here's what we can do. Let's say that we have, 10 different VLANs in this network, and I'll just put, 3 of them on a few of these switches. We'll say VLAN 10, 20, and 30 are existing on all of these switches in the network. And, you might even, I said 10, so you might even get into the 40s and the 50s and so on. Well, we've got these different VLANs running on the switch, and here's the good thing about it. In our diagram, we just saw a bad spanning tree design where this became the root bridge. We don't want that. By setting the priority, which I'm going to show you how to do, we would want one of these core switches to be the root bridge. But with per VLAN spanning tree, we can have a root per VLAN. So here's the concept. I can make both of these switches roots for different VLANs. Check it out. VLAN 10 and 20 will have this switch as their root. VLAN 30 and 40 will have this switch as their root. So what's going to happen? Well, for 10 and 20, certain links will be blocked, and, well, actually, I just X'd out completely the wrong link. For 10 and 20, we might have some links blocked that are less efficient because we'd have to go to the other core switch, which wouldn't be the root at that time. But for 30 and 40, we would have other links blocked. And what we see here is that we are effectively doing load balancing using per VLAN spanning tree. Does it take planning to do this? Yes. You need to know how much traffic has crossed each one of those VLANs and, on a day-to-day basis, how to effectively split the VLAN. So maybe, what did I say? Now I can't remember. I think 30 and 40, we're using the red links here, and 10 and 20, you get the idea. I think I just got those backwards. But you get the idea. We split the VLAN traffic to where they're using separate links, right? So we have effectively initiated load balancing. No more are links just completely blocked by spanning tree. Now they will be allowed on a per VLAN basis. It does take a little more administrative overhead, but the results are hugely worth it efficiency-wise in your network. Let's talk about the configuration of this. I'd like to start off with the foundations of spanning tree configuration, and then we'll add the enhancements to it. So I have a list of tasks on the screen, and you know me, I'm going to start at number 4, verify, by showing you the command that we use to verify that spanning tree is operational. And I mentioned the show to know at the very beginning of this nugget. Well, this is it. Show spanning dash tree. Now, in some switches, when you type in show span, it's going to look at the switch port analyzer, which is used to monitor certain ports. So sometimes span will not work as an abbreviation, but in this case, it does. I type show spanning tree, and what I see is, first off, it's focused in on VLAN 1. This is the spanning tree data for VLAN 1. Down here, I have the root ID. Who is the root? What is their priority? What is their MAC address? What is the cost to reach that root? What port am I using to get there? What is my hello timer when I'm going to that route? And all of that information about the route that's out there. Then I see myself, the bridge ID of me, this switch that I'm working on, switch A. The bridge ID is 32769. Now you might see this priority 32768. I know we talked about that, but what's this? The system ID extended 1. Back to the whiteboard we go. The first thing you must understand is that spanning tree has been around for quite some time and has gone through many different revisions. And in the original spanning tree design spec, when it was deciding who the root bridge would be, it did it through 2 things, and you already know those. Sorry about my odd-looking box. But we had the priority, and if the priority was tied, then we'd rely on what? The MAC address, right? So we have 2 things used to help decide what the root bridge would be, and this would be known as the bridge ID, or the bid. Now, the priority is any number from 0 to 65,535, which when you look at it, you're thinking, wow, that's a big range. And it takes a full 16 bits to represent those numbers. So a priority is 16 bits. Now a MAC address we know is 48 bits in length. So by combining these 2 together, we can figure out who would be the root bridge. But here's the question. Why on earth do we need that kind of flexibility? I mean, were you really thinking of having 65,535 different levels of switches in your network? No, nobody would. There's no network that even has that many switches. So with the newer versions of spanning tree, we see our packets designed like this. And of course, since we're working with the 3550 series switches, we're of course going to run the newer version. We now have the priority over on the left-hand side, and that is going to be consisting of 4 bits. In this middle section, we see a new field called the Extended System ID. You'll see it abbreviated just like that many times, EXTSYS-ID, and that is 12 bits in length. So what we did was split that 16 bits of priority into 2 separate areas. From there, we have our standard MAC address, which is still 48 bits. That will never change. So here's the difference, and here's what that Extended System ID is all about. Switches that are running this version of spanning tree will only allow you to change the priority in increments of 4096. Perhaps you've done that on a switch before. You've gone there and set the priority and it says, oh, nope, sorry, you have to use an increment of 4096. And you go, well, wait a sec, I don't remember having to do that on my old switch. Well, you didn't have to because it was a full 16 bits of priority and you could pick any number that you want in there. But here's the idea. When you have increments of 4096, the leftmost 4 bits of that priority will always change based on those increments. I think the next one is 8192 2, but don't quote me on that. But that's, I mean, I believe that's the next level of priority if we add another 4096. And what that will do is that will change the leftmost 4 bits of these 16 bits. So even though we're running the newer version of spanning tree, you see it? We can still understand these big jumps in priorities just by looking at the left 4 bits. So what is this? What is the extended system ID? This is actually a bit representation of your VLAN number. If this is spanning tree running on VLAN 1, this will be a bit representation of 1. Using 12 bits, it's 01. Okay? These are going to be binary representations of that. And it just so happens that it takes 12 bits to get 4096. So switches supporting this extended system ID are going to support 4096 VLANs on that switch. And then, of course, we have the MAC address to break the tie. So when I'm showing you on the switch what the priorities look like, and you see, well, the priority is this plus the extended system ID, that's what the extended system ID is all about. So let me bring my switch connection back up, and I almost covered all of the red in the background. What we see here is that we have the priority plus the extended system ID. VLAN 1, so system ID extension is going to be 1. Now, if we look further into the spanning tree information, we see that fast Ethernet 0/13 is forwarding, and this is acting as the root port. And then we have fast Ethernet 14, 22, and 24 that are all connected in the same way, point-to-point connections, that are in blocking mode. They are all blocking because those would cause loops in our network. And if I hit space and continue going on through this list, I see that I have that VLAN 50, extended system ID 50. You see it now? And then I still have all of these same port situations. Right now, default state, we are doing a horrible job of using our spanning tree protocol. It is very inefficient in its use, so let's make it a little better. Thus, we come to task number 1 in our list, configuring spanning tree protocol. Let me exit out of this show spanning tree view. I'm going to go into global configuration mode. And the way that we configure spanning tree is really simple. I mentioned it's going to be simple configuration commands, but the concepts are huge to understand. So to configure spanning tree and to really set the root bridge and allow spanning tree to operate correctly on these VLANs, I will type in spanning tree followed by VLAN, what VLAN number I'd like to use, and I can do ranges and commas and separations. Let's just say VLAN 50 because I want to focus on that. And if I just want to turn it on, I hit enter. Now, while I'm on this configuration, I want to mention this because it's happened to me more than once, I'm sorry to say, is that I've been at a company and I've been talking to a network administrator, and they said, well, I was just getting spanning tree errors, so I turned it off. And when I look at their running configuration, what I see is commands like this: no spanning tree VLAN 50. Now, yes, doing this does make the spanning tree errors go away, but you are taking your life in your own hands when you do this, because what have we just done? Well, we've totally canceled loop prevention on that spanning tree VLAN. So what happens is if there accidentally is ever a looped connection in there, a redundant link, it's not going to disable it, and you're going to flood your entire switch, not just that VLAN, it's the entire switch, with just broadcast traffic that will bring it to its knees. So I hope you never end up falling into that hole of typing in no spanning tree VLAN 50, but that's how we turn it back on if it is off. Now, the second thing is to set the root bridge. Let's say I've done some analysis and I've looked at my network, and switch B is the root for all of the VLANs right now, but I just want switch A to become the root for VLAN 50. Well, what I can do is type in spanning tree VLAN 50 followed by the priority. You see this priority setting. It's the second one from the bottom, and I can actually type in a priority, and you can see this is the newer one in increments of 4096. The lower the priority, the more likely I am to be a root. However, there is a keyword command that Cisco has added called root. You see it right below the priority in the context-sensitive help. What this does is it will allow you to configure it as either a primary or a secondary root. See, Cisco has recommendations as to what the priority should be to elect the switch as root, and what the priority should be to elect the switch as a secondary root if the primary root goes down. Now we can get into the diameter and actually tell it how many switches are connected. I think it goes up to 7. Yep, maximum number of bridges between any two end nodes. And we can go up to 7, but I'm just going to keep it at the default and type in primary. Let's see what it set it to. I'm going to do a show spanning tree. And we see VLAN 1, we still have the root ID is somebody else. That's switch B most likely. But when I come down to VLAN number 50, look at what happened. Root ID is what? 24626. You see it right next to it? It's the priority. That is the priority Cisco recommends you set to be standards compliant, so you don't have, different types of priorities for different routes around your network. That is the one they suggest so that you're standard compliant. You see right below it, it says this bridge, the switch you are on, is the root. Look at my port states below. We have the designated forwarding port, which is Fast Ethernet 0/13. 14, 22, and 24 are in the now learning state. They're learning what's happening on the network, and I bet you if we just do a show spanning tree 50 to focus in on VLAN, oh, did I type that wrong? I need to type in VLAN 50, show spanning tree VLAN 50. We'll now see, look at that. All the ports are forwarding because this has become the new root bridge for VLAN 50. We have effectively begun load balancing by utilizing unutilized links up till now on switch A by making it the root for VLAN 50. There is another way of load balancing in a spanning tree network, and I don't like it. I have to confess that to you right now. It is by configuring your link costs. And you may see some other uses for doing this, but the primary one that I've seen is to manually implement load balancing in a spanning tree network. Let me show you what it's all about. I'm going to take you back to our switch topology that had all the physical connections. And let's say that this one happens to be our root bridge. What's going to happen is, as we know, all of the switches are going to find the most efficient path to that root bridge. And let's say all of these are 100 megabit per second links. I'm not going to label them all, just a few. Now, spanning tree has its own cost for each link speed, and it's not 100 for 100 meg per second link. That'd be too simple. Right here, we would have a cost of, I believe it's 19 that it uses for a 100 meg link. It's a pretty complex formula that it uses to find those link costs. So what it's going to do is find the most efficient path to the root bridge, and that's how it knows that this is the most efficient. It says, well, I could use this one, that's 19, or I could use this one, which is 19 plus 19, that's 38. I'm going to use this one, and this one ends up blocked. Well, if you were somebody that wanted to manually implement load balancing without adding multiple root bridges, without having certain VLANs for certain routes and so on, you could go into those links and lie to the switch. You could say, the spanning tree cost for this link is really 4. And it would say, wow, that's a fast link. I mean, a 10 gig link is 2, so that must be like a 5 gig link. And then we'd have to do it over here as well, because that would still be higher. So I would have to say, this one's 4. Now the switch is going to look at that and say, oh, that's a cost of 8. Well, guess who's getting blocked now? You've got it, this link. And it's going to start forwarding across this path instead. The reason I don't like it is it's just ugly. Okay, if you've got one switch, you might be able to get by with it and doing it in this manner that you want to do this to. But if you've got 8 switches, or you've got a real network with 100 switches, how are you going to keep track of this? You're going to have different costs, and it's just going to drive you nuts. So it's really best to use the VLAN method, but this is a quick, dirty approach to modify how the path is taken, and let me show you how to do it back in our configuration. I'm on switch A right now, which is the root bridge. You can see this is the root for VLAN 50. So let's jump over to switch B that has some ports blocked. Okay, I'm just going to do a caps lock, a show spanning tree. We'll just do blocked ports. And we see for VLAN 50, since we manually set the root, switch A is the root for VLAN 50, switch B went ahead and blocked its redundant links. So as of right now, Fast Ethernet 0/14 is in the blocked list, and Fast Ethernet 0/13, I can see that is a valid connection. That must be the one that's forwarding on switch B. Well, let's lie to it. Let's get into interface configuration mode, Fast Ethernet 0/14. And there's two commands I could use to do this. I could type in spanning tree cost followed by what the cost of that port is. The problem with doing it this way is it would change the cost for every VLAN. So it would say on every VLAN it is a cost of 4 if that's what I'm going to type in. And I don't want to do that. I'm just playing with VLAN 50 here. So I'm going to do spanning tree VLAN 50 cost 4. Okay? And that modifies it just for that one VLAN. Now what that's going to do is it's going to recalculate and say, well, wait a sec. Let me do a show spanning tree for VLAN 50. It's going to say, wait a sec. I have Fast Ethernet 0/13. That was the forwarding port, and I noticed that it's a cost of 19. And look at what happened. It transitioned in the background. It said, I'm going to make Fast Ethernet 0/14 my new root port. And I know it just transitioned because it's in the listening phase. If I hit the up arrow one more time, it should at this point be forwarding. See that? So if I do the show spanning tree, let me hit the up arrow a couple times, blocked ports, you now see instead of 14, 13 is a blocked port because we've modified the cost to be much more efficient for Fast Ethernet 0/14. Hopefully you don't like doing this either, because I sure don't. But that's another way of load balancing in our spanning tree network. Now that we've talked about the foundations of spanning tree, let's get into some of the enhancements, starting with my favorite, port fast. I think this is about 95% of what I do on switches that are already configured on a day-to-day basis, is enabling people for port fast. What it does is effectively turns off spanning tree on a specific port. These are going to be ports that are connected to end workstations most likely, and you don't want it to go through that 35-second boot up process to figure out that it's not a switch and things like that, because maybe the workstation powers on before then and is requesting a DHCP address, but the port isn't active yet, so it times out. That's no fun. So what we can do is go into most likely interface configuration mode and enable port fast. I'm going to kind of pair the configuration with these enhancements. Let's say I want interface fast Ethernet, we'll say 0/10, just picking one. What I'm going to do is type in spanning tree port fast followed by an enter. And some older switches it would actually say enable, but they just have disable. Now when I do this, it says, warning, this should be used with extreme caution. Do not enable this on a connection to a hub, a switch, a bridge, a concentrator, anything that could potentially have a loop back, because by disabling spanning tree, you are opening yourself up for a looped broadcast packet. It says this is configured on Fast Ethernet 0/10 as long as it stays in a non-trunking mode. And that's what we'd expect. And believe it or not, we can even enable port fast on a trunk. Maybe you have two switches linked together and you want it to come up very quickly, or maybe a router on a stick style configuration. You notice my second bullet says it should always be paired with BPDU guard. This is a pretty sweet feature, and it's done from global config mode. I'll type in spanning tree port fast, followed by, you have two options, BPDU guard and BPDU filter. Here's the idea. By typing in BPDU guard, you will have that switch be watching for any BPDU packets, which are what? Generated by other switches. So if it receives one, it's going to go, wait a second, hey, this is a port fast port. I am only supposed to be connected to an end workstation, not another switch. You're another switch, so because of that, I'm going to cut you off. Chop. And that's what I think of when I think of guard. It's just the sword comes down, chop. It cuts off the port and disables it, which means you as an administrator will know about it because you have to get back in there and re-enable the port. Now, BPDU filter, you see it above, is the kindler, gentler version of BPDU guard. Instead of cutting the port off, it just filters out BPDU, saying, you know what, you may be a switch, but I'm not even going to listen to you. I don't want you to mess up my spanning tree. I don't want you to mess up my trunking. BPDU filter just ignores any switches. The other option you see under this is a scary one. Spanning tree port fast default. It enables port fast on all access ports. Use this one with caution because it's easy to say, you know what, I don't want to go port by port and turn this on. I want to do it on the whole switch. And you forget, oh, there's that one uplink port or those two uplink ports to the other switches, and poof, you're going to toast yourself by enabling it on all ports. Be very careful if you decide to use this default keyword. But that is port fast. That is the one that most people end up using on a day-to-day basis. The other two fasts in this list, the uplink fast and backbone fast, are Cisco proprietary enhancements to spanning tree. And they're pretty neat. They came out quite some time ago. And before I even explain them, let me tell you that they're not in use very often anymore. And I'll explain why that is in just a second. Uplink fast, here's the concept. It puts ports to the same destination into uplink groups. So let's say you have redundant connections. It's going to say, okay, this is uplink group 1 and uplink group 2. And it groups these things together. And if at any time your root port fails, the one that's forwarding, it will transition to the other port in the uplink group right away. Well, I should say in approximately 5 seconds failover time. Compared to what it is normally, that is amazing because normally it has to go through a full 50-second process. It has to go retransition all the ports to the blocking state, go to the learning state, and really kind of discover the network again. But with uplink fast, it gets proactive and it says, I know that's a redundant link, and I know if this one goes down, that one should be used. So it reduces your time from somewhere around 50 plus seconds to around 5 seconds. Pretty neat, huh? Now, backbone fast is, I needed a topology to explain it. It's just an odd scenario that happens. Here's the idea. It says allows faster recovery from indirect link failures. Let's say that this is the root bridge, and this link goes down. Now, if this one, it has the second priority, meaning it's second in the list, it's a backup route. If this link goes down, it's going to assume the entire root bridge goes down. Now, that may or may not be true. It may just be the cable has gone bad or someone pulled it out. But this one immediately will start saying, I'm the root, because my main link went down to the root. So it's going to send out, I'm the root messages or BPDUs to this switch, who's then going, huh, that's funny because the root up here, which has a higher priority, is still online. That's without backbone fast, because what will happen is this port will have to go through all the forwarding states and the transition states and so on when it receives that message, and this guy stays hung thinking it's the root for the longest time. Not so with backbone fast. Backbone fast allows this switch to correct the confused root switch. It's going to send an inferior BPDU saying, hey, I'm the root. This one's going to say, no, you're not, and it's going to return a BPDU saying, this is incorrect information. Here is the real root message. And this guy goes, oh, I'm sorry, I was wrong. It's a polite switch, obviously. And it will transition, it will say, I must not be the root, and instead, I will have my root port be this port. Now, it's not as efficient as uplink fast, but it does improve your recovery time because instead of just waiting to find out that it's not the root on the normal BPDU update schedule, this switch gets proactive and updates it for it. Now, to configure these, it's very simple. All we need to do is just one command. It's a spanning tree. If you want to do uplink fast, you just type in spanning tree uplink fast. If you want to do backbone fast and enable that, you just type in backbone fast. That's all there is to the configuration. But do remember, these are Cisco proprietary enhancements to the spanning tree protocol. But it's already time to say, move aside Cisco proprietary enhancements and make way for Rapid Spanning Tree Protocol, the new standard, 802.1W, which will eventually replace 802.1D on all switches. Now, does that mean all those proprietary enhancements we just talked about aren't valid? Well, no. If your switch only supports just supports 802.1D, which is Spanning Tree Protocol, they work great. However, this is a newer method that integrates all the Cisco proprietary features that we just discussed and even makes them better. So you're going to see things that look like uplink fast, things that look like backbone fast, but they even converge faster. There is still port fast as well. However, you probably won't have to use it anywhere near as much as what you used to because Rapid Spanning Tree can activate a port much faster. In my experience, I've found it goes up in around 5 seconds for a normal workstation, and my workstations can boot fast, but not that fast to outdo rapid spanning tree protocol. So how does it do this? How does it become more efficient than the standard spanning tree? Well, there's actually tons of white papers and documentation on how it works, but here's the essentials behind it. Number one is it lowers the number of port states. Instead of having 4 of them before, and each one taking a certain length of time, we have 3 of them, and there is no fixed length of time really assigned to each one. We have discarding, learning, and forwarding. There's no listening and blocking and all that like we had with the normal spanning tree. The other thing is that they've actually created port roles and differentiated between these two. Just because a port is discarding doesn't mean it's not a designated port. It'll blow your mind when you get into the architecture behind it. You combine your port states with your port roles. And here's the port roles, and most of them we already know. Root port, best way to reach the root. That would be that port designated as the root port. Designated port is just a port that most likely is designated to be forwarding, maybe on a segment that's not connected to the root, or a segment that's forwarding to allow another switch to reach the root. Now these two can boggle the mind. Alternate port and backup port. Matter of fact, let me even draw a small topology over here, because every time I see those two I think they sound like the same thing, right? Well, let's say this is our super root switch up here, and we've got switches connected to, these are just normal switches, connected to the same segment down below. Okay, with this one having redundant links. An alternate port would be one that is selected essentially as a backup. I can't think of another way to say it. It's an alternate to reach the root. This would most likely be the root port, right? Because it's directly connected. This would be an alternate to reach the root. So with this, I'll put root port over here. This is an alternate to reach the root. Now a backup port is kind of like when we discussed uplink groups just a slide ago. It's kind of that same concept. We have another port on the same segment that could be grouped together. It's kind of like a backup alternate port, if that makes sense. I know it's wild, but here's the scenario, and this will make sense. Let's say our root port goes down, right? Poof, it's toast. This one becomes now, instead of an alternate, that's the root port, and guess what happens to the backup? You got it. It becomes the alternate. So you see how kind of we have double redundancy in place on some of these switches. Finally, disabled port, just what it sounds like. If we've got, you know, a secondary, well, you know, it's hard to find a disabled port nowadays because it's typically going to be labeled as an alternate or a backup. But if you have a redundant link in place that isn't one of those two, it will just be a standard disabled port. Any switch running an iOS capable of handling rapid spanning tree will have it enabled by default because it is backwards compatible with 802.1d. So if you have a non-rapid spanning tree switch connected, it can work with it. You just lose a lot of features by doing that. But if for some strange reason you wouldn't want to use it, you can just go into global config mode and type in spanning tree mode, followed by what mode you'd like to use. And really the two that most people use are going to be this one, which is on by default, per VLAN rapid spanning tree, or just per VLAN spanning tree. This is the old mode of doing it. Between those two modes, there's no reason that I can think of why you wouldn't use rapid spanning tree on a per VLAN basis, since it is indeed backwards compatible. Just to ensure that I hit all of the items in this list, MST is multiple spanning tree mode. This is a pretty wild one that allows you to have one spanning tree instance for multiple VLANs. It pretty much limits the amount of resources your switch has to consume, since multiple VLANs really usually have a similar topology look and feel. You can share spanning tree instances using that. However, my definite preference is using rapid per VLAN spanning tree. Fantastic nugget. What we have talked about is all about the spanning tree protocol and how to design your network efficiently to work with the spanning tree protocol. We got into the configuration, which isn't too bad once you understand the concepts, and then we looked at the enhancements, both Cisco proprietary and now, with Rapid Spanning Tree, industry standard. And of course, the show to know that I always use. There are more show commands that you can use, however, the one I always use because it displays so much good info is show spanning dash tree. Gives you just about everything that you'd ever need about the spanning tree protocol. I hope this has been informative for you, and I'd like to thank you for viewing.